Okay, here comes a wave. Up, down, up, down, up, down, up, down, up, down, up, down, blah, 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 blah. Okay, how fast my pencil was moving forward there is the velocity of the wave. If this was a vacuum and that wave was light, it would be moving with a very particular speed called c, which is 3 times 10 to the 8th meters per second. But of course, in other materials, which we learned with Snell's law, that speed can slow down. How slow it's going is determined by the index of refraction. The higher the index of refraction, the slower the wave of light is going. How quickly or how fast I was moving my pencil, wiggling it back and forth, is called the period. So the amount of time it takes me to go from trough or from peak to peak, or from a trough back to a trough, that is called the period. Okay, it's measured in seconds. Okay, how long? Okay, how many wiggles I make every second is called the frequency. And the number of vibrations per second is, of course, hertz. Okay, we've learned all this before. Keep in mind, too, that the longer the period is, in other words, the longer it takes me to make one wave, the shorter the frequency is going, or the smaller the frequency is going to be. Those are inversely proportional to each other. So if your period of time is longer, your frequency will be slower, or will be lower. If your frequency is higher, your period will be shorter. And last but not least, wavelength. Wavelength is the distance from a peak to a peak or a trough to a trough. And of course, we use the symbol lambda for that, and it's measured in meters. One thing that does not come up a lot is actually the amplitude of the wave. And this is actually the thing that you probably most physically aware of when you're in an ocean, something like that. It's, if you imagine a dead flat lake or an ocean, nothing's moving. And then, wind kicks up, so you start to get swells of water like this. Okay. Amplitude is the height from equilibrium of that wave. How do we experience these different things, with our senses? Because the human body is equipped to pick up all these different parts of a wave without us being really aware of them. Well, let's talk about, first of all, frequency and wavelength. Now, frequency and wavelength are basically cousins of each other. If you know frequency, you know wavelength, okay? They're like conjoined twins. If you know one, you know the other. People forget this all the time. They'll be given a problem with a wavelength and they'll really want the frequency. They get so frustrated. They're like, why didn't they give it to me? Well, remember, you always know them because you're always going to know that wave equation, which we'll talk about in a minute. C is equal to F lambda. So if you know the wavelength, you always know the speed of light. So in a vacuum, you could easily find out what the frequency is. But that's not really how we experience it, okay? Let's talk about it. So let's say right now I am going to have a little patch of blue on your screen here. Okay, so what is that? Why are you seeing blue at all? Well, what's happening is your computer screen is putting out light that is a wavelength of approximately... it's like 460, 470 nanometers. Okay, so we have 460 nanometers. So in other words, that's how long each wavelength is. If I were to have a patch of red, that would be your computer screen putting out a wavelength of approximately 650 nanometers. So something longer. Okay, blue is actually the energetic color. Red is one that has a longer wavelength and a lower frequency, and therefore it's going to have less energy. So we think of red as being very exciting, but it's actually the slow, lazy color. Blue is really the one that's exciting and pepped up. What is amplitude to you? Well, if you're talking about sound, well, first of all, I should say from the previous thing, if you hear a frequency, in other words, instead of going as a light, but you come as a sound, frequency is the sound of your voice. That's me changing the frequency of my voice. Amplitude is how loud I sound. So the higher I can make the amplitude of my voice, the louder it's going to get. In terms of light, you would call it the intensity, or you think of it as the brightness of the light. Okay, the wave equation is the velocity is equal to the frequency times the wavelength, or V is equal to F lambda. You frequently see it written like this because we're very often talking about light in a vacuum, but not always. So you should keep that in mind. If we're dealing with sound or something like that, you'd have to know the velocity. One other very key idea that we're going to get into in more and more detail here is that energy of a wave is proportional to the frequency. People often feel it's going to be the speed, so the faster that the light is moving, the more energy it has. That is not true. It's actually how many wiggles you have per second that are going to be proportional to the energy. And you can kind of feel this. If you imagine taking a slinky and going with your hand going back and forth, that doesn't take a lot of energy. However, if you're going to take the slinky and you're going to go back and forth, back and forth, back and forth, back and forth, that's going to take a lot of energy. Okay? We're very often in this section going to be talking about small amounts of energy. Small amounts of energy, or joules, which is already a pretty tiny amount of energy, is going to be so huge it's basically useless. We're often going to measure things in something called electron volts. And you're like, oh, something else to memorize. Well, don't worry, because these guys are super easy. Electron volts actually kind of say their name, or they say their calculation. So let's say we had 2 electron volts and we wanted to know how much that would be in joules. We'll actually just write it out. 2 and then electrons, so you can multiply that by 1.6 times 10 to the negative 19th. Just like, the charge of an electron. And that actually gives you the value in joules. So if you put that in your calculator, you get 3.2 times 10 to the negative 19th. That's how many joules 2 electron volts were, okay? So these are really, really super small.